Hello everyone. In the last video we saw how we can find the time complexity of any complex for loop algorithm, and in this video we are going to continue that. So let's start. So here is our next example where we have nested for loops and we have to calculate time complexity of this for loops. Now you will say that this algorithm is of order of n square, but let's see. Here our for loop is running, and inside inner for loop is running with condition that j is less than I. What that means, let's see. So here we have I, j and number of times our statement executed. First, I is initialized to 0, we will write here 0. Then j is also initialized to 0, we will write here 0. But if we check the condition for inner for loop, here it's saying that j must be less than I. But j is 0, I is also 0, and 0 is not less than 0. It's equal to 0. They are equal, not less than or greater than. So you can say that number of times statement executed is 0. Next our I will become 1, and then it will check the j condition that 0, j is 0, 0 is less than I is 1, 0 is less than 1. So yes, j becomes 0, and number of times the statement executed this time will become 1. Then j will be incremented and become 1, but this time statement will not execute because 1 is not less than 1. Then I becomes 2, j becomes 0, number of times statement executed is 1. Then j becomes 1, incrementing after number of times statement ran, because 1 is less than 2, so it will execute one time. Then j will become 2. This time 2 is not less than 2, so it will not execute, it will return 0. It will be executed 0 times. So if we separate them, we can see that when I is 0, statement number of times statement ran is 0, and when I becomes 1, the number of times statement ran is 1. Then I become 2, number of times statement ran is also 2. Following this pattern, if I becomes 3, we can say that number of times statement will run will be equal to 3. So looking at this pattern, we can say that if I becomes n, statement will also execute n times. So here we can say that our time complexity is big of. So next example is a for loop where it is not incrementing or decrementing, it's just multiplying, and I is initialized to 1, so 0 does not occur any times. Let's see. Here we have I, and I is firstly 1, then I will become 1 into 2, which equals 2. Then this 2 will come here, this 2 will come here, and it becomes 2 into 2, which equals 2 square, and this 2 square will come here and multiply by 2, which becomes 2 cube, and similarly it will keep going until we get, so it will keep going until we get 2 to the power k, not n. I'm using here k, and now let's assume that our I has finally become greater than or equal to n. We are assuming this for our for loop to stop, so that we can find the time complexity finally. So I is what? I is 2 to the power k, to the power of k greater than equal to n, or we can just say that 2 to the power of k equal to n. Now if we take log with base 2 on both sides, this will become k equal to log n base 2. So that's the time complexity now. Here we have k, and the time complexity is order of k, or we can write it big O of log n base 2, or order of log n base 2. Similarly, if here we had I into 3, then what will time complexity be? 1 into 3, 3, 3 into 3, 3 square, 3 square into 3. Then similarly, it will be 3 to the power k, and 3 to the power k equal to n, k equal to, if we take log of base 3 on both sides, it will be k equal to log n base 3, and it will become order of log n base 3. Now let's take a look at our next example. Here I is initialized at n. It will run until I is greater than equal to 1, and the condition here is I is divided by 2 each time. Now let's test it. Here we have I. Firstly, I is n. In the next turn, n is divided by 2. Then in the next turn, n divided by 2 is again divided by 2, which equals n divided by 4. Now this n divided by 4 is again divided by 2, so it becomes n divided by 8, and it keeps going and becomes n divided by 2 to the power of k. So for our stopping condition of this loop, we can say that I is less than 1, because we are saying that I will run until I is greater than equal to 1. So we can say I is less than 1. I is what? N divided by 2 to the power k. N divided by 2 to the power of k, and we are assuming that it will be equal, will be approximately equal to 1. Now let's send the 2 here to the power a k here. So it becomes n equal to 2 power of k. And if we take log base 2 on both sides, it will become log n base 2 equal to k. So similarly, from our previous example, we saw that like this. So again, it is just in reverse. We can again say that time complexity of this is order of log n base 2. Here we have another example where I is initialized to 0 and I is incrementing. But here's the twist. In your condition, it's I into I, which is less than n. So let's set the ending condition of this loop, which becomes I square greater than equal to n. So we can say I square equal to n. To find a time complexity is approximately equal. Then we can say that taking square root on both sides, it will become I equal to under root n, and the time complexity from here we can calculate. It's order of root n. So we have a time complexity for this algorithm. So here is our another example where we have two for loops. They are not nested. What do you think the time complexity will be? Order of n square? No. Let's see. For this for loop, we can say that it will be order of n, and for this for loop, we can again say that this will be order of n. Now, if we sum these, what do you think that time complexity will be? 2 times order of n or order of 2 times n? No, it will still be order of n only. So here was the next example where we have condition from all different cases we have learned just now. So let's see the second statement. Let's assume that p is some large number. So here we can say that this statement will run for order of log p base 2, because here in this condition we have p. Then let's say this one for loop, this for loop, we can say that p will be equal to log of n, because it depends on n. Whatever values n becomes, p will take them. So finally we can say that this whole algorithm will run for order of log p times. And what is our p? We got it from here. P is log n. So our final time complexity will become, it will become log of order of log n. With base 2 we can add whatever number we have here. If it's 3, then it will become base 3, something like that here also, because they're both base 2. So we can just say that it is of order of log of log n, This is our time complexity. So now let's see our last example of this video, where we have a nested for loop with the inner for loop having variable multiplied by 2. So we can say that from here, this statement will run for log n times, also base 2 if you want. Then this for loop will run for n times. If this inner for loop is running for log n and this outer loop is making it run for n times more, we can write here it will be log n into n. So our final time complexity becomes order of n log n. That's the time complexity of this algorithm. So that was all for today. In the next video, we will see how we can find the time complexity of any while loop. Thank you.